Let's return for a moment to our definition of torsion as a twisting moment applied along the axis of a shaft. To annotate torsional loading on a given shaft, we can first draw its axis, and then the pair of twisting moments that react each other along that axis. As engineers like to talk in scalars rather than vectors, we need to establish some form of sign convention for these torsional moments. Enter the right hand grip rule. Taking your right hand in a gripped thumbs-up position, align your thumb with the axis of the shaft, with the tip of your thumb pointing in the outward normal direction of the shaft section. With this alignment complete, your grip fingers point in the direction of a positive torsional moment. Returning to our cylindrical shaft on the right, we see that according to this rule, the rightmost torsional moment is positive due to the outward normal of the shaft pointing to the right, and the torsional moment on the left is also positive due to the outward normal of the shaft pointing to the left. Creating three-dimensional representations of torsion moments in a two-dimensional drawing space can often lead to confusion. To prevent this, a simplified notation of a double-headed arrow is often used to denote a torsional moment. Here, the direction of the arrows align with the pointing direction of the thumb in the right-hand grip rule. Torsion. It is a form of loading that quite literally has the potential to propel us in life. It is a powerful loading for any engineer to master. And now that you are equipped with the notation and sign convention to describe it, we can dive deeper into understanding the effects of torsion on the deformation, performance, and failure of engineering structures.
On the surface of the shaft, I have drawn 4 lines around its circumference, distributed equally along its length. Additionally, a line parallel to the axis of the shaft has also been drawn on the surface. Observe what happens to these lines when an alternating torsional load is applied to the shaft. 2 observations can be made. First, the 4 circumferential lines rotate but do not displace or distort. Second, the line along the axis of the shaft rotates through an angle but remains straight. By adding 2 more lines to the surface of the shaft, a rectangular element can be defined. Repeating the alternating torsional loading, the nature of this deformation becomes more apparent. As the lengths of the sides of the element do not change, it can be concluded that the element does not experience any normal strains. However, the element does rotate through an angle just as a square element subjected to pure shear would.
Let's take a closer look at what is happening on our circular shaft of radius r. Consider a square element ABCD on the surface of the circular shaft as shown here. For illustrative purposes, we have drawn the element large and visible. However, we are going to analyze it as an element of infinitesimal width dx. Let's first isolate the portion of the shaft containing our infinitesimal element. As we ascertain from observing shear deformation in our foam shaft, torsion creates a state of pure shear. Thus, if we apply a torque T to our segment of shaft, the square element ABCD will undergo shear deformation, resulting in infinitesimal rotation of the shaft segment d phi. This angle is equal to the rotation of point B relative to point A along the axis of the shaft. On the surface of the shaft, our infinitesimal element must shear by angle gamma to be compatible with this deformation. This angle gamma is exactly the shear strain experienced by the element. Geometrically, we can relate the tangent of this angle gamma to the ratio of the length B prime over length AB. Length B prime is the arc length swept by radius r through infinitesimal angle d phi, or r times d phi, and length AB is simply the width of our element dx. Since we expect shear strain in real materials to be small, we can apply a small angle approximation where the tangent of our angle gamma is approximately equal to the angle itself in radians. Applying this approximation to the equation above, we can rearrange it to obtain that the shear strain gamma is equal to the infinitesimal angle of rotation of the segment d phi divided by the infinitesimal width of our segment dx, multiplied by radius r. In the previous slide, we examined the shear deformation on the surface of a segment of our shaft. Let's rename the shear strain at this location to gamma max and take a look at what is happening inside the segment at an arbitrary radius rho. Extracting the interior portion of our original segment at radius rho, we see that the surface of this extracted segment also undergoes shear deformation. Using the same approach as before, it is easy to see that the shear strain gamma at this new radius rho will have a similar relation to d phi and dx. This expression can be rearranged in terms of the outer surface shear strain gamma max, resulting in the expression rho over r times gamma max. From this simplified expression, it becomes apparent that shear strain varies linearly with radius rho, starting from 0 at the center of the shaft and increasing to a maximum at the outermost surface of the shaft. In order to transform the strain distribution into stress, it is necessary to recall Hooke's law for shear as shown here. It is also necessary to visualize the pure state of shear stress acting on our infinitesimal element that will cause the shear deformation we observe. Finally, we must recall the linear shear strain distribution from the previous slides. Rearranging Hooke's law for shear stress and substituting in our shear strain distribution, we can see that the shear stress distribution also varies linearly from 0 at the center of the shaft to a maximum at the outermost surface. Slightly less obvious is that due to the concept of complementary shear stress and the state of pure shear illustrated in our element in the center of the slide, this shear stress distribution describes a shear stress acting perpendicular to the radius over the cross-section of the shaft, as well as the shear stress acting in the direction of the axis of the shaft as illustrated on the right. This resulting shear stress distribution, again, is a result of the principle of complementary shear stress.